Hello, so this is a revision video for IB Chemistry S2.2.12, Benzene and Resonance. This is for AHL students only. Benzene is an unsaturated hydrocarbon with the formula C6H6 and a planar hexagonal structure. Historically, benzene was described by something called the Kekulé model, where each carbon atom formed alternating double and single carbon bonds in a ring-like structure. However, experimental evidence shows that all carbon-carbon bonds in benzene are identical in length, and the bond length is somewhere between a single and a double bond. Because remember, single covalent bonds are slightly longer than double covalent bonds. So if benzene has alternating double and single carbon bonds in its structure, we would expect to measure two different carbon bond lengths when we look at the molecule. However, the fact that only one bond length is measured, and it's somewhere between a single and a double bond, means the alternating double and single carbon bonding proposed by the Kekulé model can't be completely correct. Instead, the actual structure of benzene is now better described as a resonance hybrid, shown as a hexagon with a ring in the middle of the carbon atoms, representing delocalized pi bonding electrons. The delocalization of pi bonding electrons comes from the sideways overlap of unbonded p orbitals from each carbon atom. When forming benzene, each of the carbon atoms single bond to each other and one hydrogen atom. This means each carbon has one electron left over that's unbonded. The unbonded p orbitals from each carbon atom, with one electron in each, can overlap sideways to create two rings of electron density above and below the carbon atoms bonded together. This means all the carbon-carbon bond lengths in benzene become equal because they have equal access to electrons, and the structure is actually slightly more stable than we'd expect it to be otherwise. For example, enthalpies of hydrogenation show that benzene is more stable than we'd expect, especially when compared to the theoretical Kekulé model, which would have a name cyclohexane-135-triene if it existed. When cyclohexene is hydrogenated and its double bond is converted into a single bond to make the molecule C6H12, minus 120 kilojoules per mole of energy gets released. In other words, the cyclohexane C6H12 is 120 kilojoules per mole more stable than the cyclohexene. Well, cyclohexene contains one carbon-carbon double bond. The theoretical Kekulé model of benzene contains three carbon-carbon double bonds. So, if 120 kilojoules of energy is released when the one double bond in cyclohexene is hydrogenated, we would predict that approximately 360 kilojoules per mole would be released when the three carbon-carbon double bonds in the Kekulé model of benzene are hydrogenated. But actually, when benzene is hydrogenated to form C6H12, only 208 kilojoules of energy are released. The fact less energy gets released when cyclohexane is formed from benzene means that benzene must be lower in energy and more stable than we predicted in the first place. And this is explained due to delocalization energy. There is also chemical evidence which goes against the Kekulé model of benzene. Alkenes, which are hydrocarbons that contain a carbon-carbon double bond, undergo addition reactions. However, benzene undergoes substitution reactions. This is because in a substitution reaction, the ring of delocalized electrons can be maintained, which increases the stability of the structure. In other words, benzene doesn't undergo addition reactions because that would mean breaking apart the ring of delocalized electrons permanently, and that would make it less stable. Exam tip here. Make sure you can explain why we now propose the delocalized electron model of benzene and its resonance hybrid structure. Use the evidence of equal bond lengths, hydrogenation enthalpies, and its tendency for substitution rather than addition in chemical reactions. And always remember that the theoretical Kekulé model doesn't actually exist.